Get out your notebook to practice this stuff. You can label the page with your problem numbers or your learning objective number. We're looking again at constitutional isomers and identical molecules represented in different formats. Or maybe they're not the same molecule. You've had practice drawing things as line angle structures, so let's do that again. For the first carbon, I put my pen down, draw to the second, draw to the third, to the fourth, branch going up, continuing on, and one more, and then that carbon, instead of being attached to H's, is attached to an O and another O, which is attached to an H. So it's a carboxylic acid that hopefully you recognize by now with your practice identifying functional groups. Let's go on to this one. Carboxylic acid again there. But this time I've got a CH3 connected to a CH2, and there are two of those all connected to this C here. So there's CH3, CH2 to that C, but then I've got another one, CH3, CH2, CH. Connected to a CH2, connected to a C, carboxylic acid. Let's look over at this space filling model. Well, here we've got the carbon connected to an oxygen and a carbon connected to an oxygen connected to a hydrogen. So, got a C, and we have to deduce that that is a double bond to an O because we know carboxylic acids and because we know oxygen likes two bonds and we don't see a hydrogen on it. Let's continue on to this carbon. And I'm doing this not as a line angle structure, so I'm going to have to redo it again. Down to a carbon there, up to that carbon, now in this picture I see two H's here, two H's here. I don't see any H's there. I see two here, two, 1, 2, and maybe 3. So space filling models hide atoms sometimes depending on your angle. So we know that on the end of a chain, carbon has to have 3 H's. And we know that here, this carbon has 3 bonds to carbon. It's got to have an H that we can't see hidden behind it. So that's something to get used to if you're looking at a lot of 3D structures. But now I'll do it in a small line angle. Okay, now everything is a line angle structure. I'm going to do a second step and number things. When I'm numbering, I'm going to start every numbering so that it begins with my carboxylic acid as 1. So up here, 1, 2, 3. Now, this is a longer chain up top, so I'm going to go up 4, 5, 6. Over here, I'll start with the carboxylic acid. Down here, again. Now these chains are the same length, so I'll just pick one of them. Down here, longer to the left, here, and this last one, I'm going to start closer to the double bonded O, because that's a group that would get priority, but as long as you're consistent, this is not a carboxylic acid. It's 4 if I go from this carbon, it's 1, 2, 3 if I go from this, so I'm going to start over here. Now that I've got the numbering, I can identify functional groups and what their numbers are. I've got a carboxylic acid there. Carboxylic acid. So those 5 molecules all have carboxylic acids. This one instead has an alcohol and a ketone. I can also identify side chains. This is not on my main chain. And since you've been doing all this practice identifying functional groups, we can label these. This first one, a carboxylic acid, I'll abbreviate. Not a standard abbreviation, but it's at 1. Here, again, at 1, I've got a carboxylic acid. Here, at 1, I've got a carboxylic acid. 1 carboxylic acid. 1 carboxylic acid. This molecule, on the other hand, has at 3 a ketone, and at 6 an alcohol. So everyone that has a carboxylic acid at 1 has the potential to be an identical molecule, or they could be constitutional isomers. We don't know yet. But this one down here is definitely not an identical molecule, but it still could be a constitutional isomer if it has all the same atoms as the others. So let's do the alkyl side chains. Here we've got 1 carbon, so methyl at 3. Here at 3 we have 2 carbons, so it's 3 ethyl. So those are definitely not the same. Here at 4 we've got a methyl. Let's go up here. That's 3 methyl. Down here, 4 methyl. And on this one we have 2 methyl. And we've highlighted here. So, for things to be the same, they have to have the same functional groups. Let's identify these. That's our molecule A. Call this B, C, D, E, and F. So A has 6 carbons in its chain. That's true of C, of D, and of F. So by the carbon chain, A, C, D, and F could be the same. But then let's look. A has a carboxylic acid at 1. C also. D also. F no. So now we're down to A, C, D. Let's look at the side chains. 3-methyl. That's different from 4-methyl. Forgot my L on the end there. But that's the same as 3-methyl. So we've got A equals D. Those are the same. If we want to decide if things are isomers, the groups don't have to be the same, but the number of carbons do. So total carbons. A has 6 plus 1 is 7. B has 5 plus 2 is 7. C is 6 plus 1. We know D's the same. E is 7 plus 1, so it's 8. So I'll write this down. 7 carbons on all of them, except for E, which is 8, and F has 6, and 1 is 7 carbons. I don't have all the H's written out, and in theory I'd have to count all the H's, but I can look and say, here we've got 2 O's. Same here, 2 O's, 2 O's, 2 O's, 2 O's, 1, 2, 2 O's. And I can count the number of double bonds or rings or triple bonds, things. This has one double bond, one double bond, one double bond, because double bonds take away hydrogens. One double bond, one double bond, one double bond, and there, one double bond. So now everything with the same number of carbons, oxygens, and double bonds will be a constitutional isomer. And you may have noticed that everything had 2 oxygen, 1 double bond, but only one of them has 8 carbons. The others all have 7. So A, B, C, and F, B, C, and F are all isomers. Constitutional isomers of A. Now, are any of B, C, or F identical molecules? Well, B has an ethyl group there instead of methyl groups, and F does not have a carboxylic acid, so they are all isomers of each other. And I could have included D. They're all isomers of D as well, B, C, and F. But A and D are identical, so it's an unnecessary thing to state.